Okay, here it is, bonding part 2, which is covalent bonds. I guess that would make part 1 ionic bonds. To get to covalent bonds, we need to answer a question. Why would atoms ever want to stick together? And the answer, of course, is to achieve an octet, to gain an outer s2p6 configuration. So that's 8 electrons, an octet on the outer shell, the valence electrons. So anytime an atom can lose, gain, or share electrons in order to get that octet, then you will have a chemical bond. So first let's review ionic bonding. In the ionic bond, we know that electrons are lost or gained to achieve that octet. That formation of ions means there is an attraction due to having opposite charges. For example, potassium has only 1 valence electron, and fluorine has 7 valence electrons. So what's going to happen when fluorine and potassium react with each other? Fluorine needs to get 1 electron to get its octet. Potassium needs to give up an electron, allowing its s2p6 configuration just below the outer electron to become valence electrons and thus an octet. So what's going to happen here? And that's exactly what we predicted. Fluorine now has its octet. Potassium has its octet. But potassium is positively charged. It lost an electron. Fluorine is negatively charged. It gained an electron. So that positive-negative attraction is the ionic bond. So what are covalent bonds? In covalent bonding, the octet rule still is in place. They want to achieve a noble gas configuration, the octet rule, an outer s2p6 configuration. But rather than losing or gaining electrons, the octet is achieved by sharing electron. And a shared electron pair is called a bonding pair. Let's see how that works with chlorine. Chlorine is one of the diatomic molecules. It can form a covalent bond with itself. If we look at the dot structure, chlorines have 7 valence electrons. They each want to gain 1 electron, but they're both highly electronegative. Neither one will give up an electron. They both want to gain. So the solution is that they can share their electrons. So now, each chlorine, if they both count the electrons that are being shared, they will have an octet. And the electrons in the middle are the bonding pair. So that pair is shared. And the bonding pair, it's a single bonding pair, and it's called a single bond. So this is covalent bonding. Covalent. Co, together, valent, valence electrons. The sharing of electrons to achieve an octet, to achieve a stable noble gas configuration. And a dash is used to represent a pair of shared electrons, and so the single bond can be abbreviated between the chlorine atoms with a dash. That represents the single bond, the single pair of electrons. Okay, here's another diatomic molecule, oxygen, O2. Each oxygen only has 6 valence electrons. It needs 2 more, and again, they're both highly electronegative. They're not going to be wanting to give up any electrons. What's the solution? They each have 2 unpaired electrons. Let's see what's going to happen here. I think we've got a solution. If you can draw a circle around 8 electrons, including the shared electrons, then you've succeeded in creating a stable molecule. So here, each oxygen has 6 valence electrons, and you add the 2 shared electrons, that gives a full 8 outer electrons. And so the other oxygen does the same, and so together, sharing 2 bonding pairs, they each have an octet. That's a double bond, and so 2 dashes represent the 2 pairs of electrons that are in the bond. So this is the oxygen molecule O2. The cool thing about covalent bonding is that it allows for an amazingly large variety of compounds. Much more than ionic compounds. The amount of ionic compounds are limited by how many combinations of metals and nonmetals we can get, and that is a finite number. But the thing with covalent compounds is that you have carbon being able to constantly build on itself. So every time you add another carbon or nitrogen or an oxygen or a group of atoms onto a molecule, you've created another molecule, and you can just keep on going. So some simple examples: water, H2O, carbon dioxide, CO2, alcohol, this is the kind of alcohol that people actually put into their body, C2H5OH. And then we have somewhat larger compounds such as aspirin with 21 atoms. Here are the sex hormones. Estrogen is a class of hormones, and estradiol is one of them. And of course there's testosterone. One thing that's really fascinating about these two molecules is how similar they are. If you look at the atomic structure of estradiol, there are 3 6-carbon rings and 1 5-carbon ring, and that's exactly what we see with testosterone. So there's not a lot of difference between these two molecules. They both have oxygens at either end, and there's not a lot of difference in the amount of atoms. 44 atoms in estradiol, 49 atoms in testosterone. And this is the molecular basis for the very well-known fact that very few people know, that it takes women less material to do the same amount of work as men. One of the more amazing facts coming out of molecular biology. And actually, on a more serious note, both molecules are synthesized in the body from cholesterol. Cholesterol has the same ring structure as estrogens and testosterone and all other steroid hormones. And actually, one thing you should notice, all the gray atoms are carbons, and the red is represented by oxygen. So if we go back and look at all these molecules that we've been looking at, they're always, except for, of course, water, many of them, especially as we get to larger ones, they always have carbon in them. You can keep on building larger and larger molecules with carbon. Let's go to some larger ones. There are 30,000 proteins in your body. Actually, that number depends on how you define proteins. If you define it simply as how many genes there are that code for proteins, there's about 30,000 proteins. One of the smallest ones is insulin with 778 atoms. A very large one is hemoglobin with about 11,000 atoms. And then you have even larger molecules like DNA with millions of atoms. Look at all the gray atoms in there. Those are all carbon. So carbon is the king, and we can just keep on adding more and more carbons, a few nitrogens, sulfurs, and oxygens here and there, and of course hydrogen, and just keep on building and building and building more covalent compounds. And there's an estimated 10 to the 40th possible compounds containing up to only 50 atoms. So you can imagine the amount of compounds that people can come up with. And that's exactly what the chemical industry does. As of a few years ago, there were 31 million known compounds, and 12.5 million of those commercially available. Thousands of new compounds discovered or synthesized every week in the chemical industry or discovered in the research communities. So covalent bonding is one of nature's most amazing inventions.